Hello, everyone. Good morning, and a very warm welcome to today's webinar on superconducting qubit design. We're going to talk about the techniques, the tools, and some real world applications. My name is Sharath, and I work as a senior account manager at Keysight Technologies. We Keysight, along with our partner InfiniPoint, we're happy to welcome everyone to this exciting session today. I think everyone present here have been hearing about quantum or has worked in the field of quantum. And it's because it's becoming the real buzzword today, right? Only next to AI ML today, and quantum is the next big thing. Quantum computing used to be heard in books and theoretical research all these days, but now we have actually started looking into real world hardware implementation. And that's where, you start moving towards real world hardware implementation. You need some access to accurate design tools, high fidelity tools that's becoming more critical today, right? So that's the most critical aspect of any designs. And so today we will explore eSight ADS's Quantum Pro, and that enables design, simulation, optimization of superconducting qubits, specifically also on the cryogenic amplifiers, because superconducting qubits and cryogenic amplifiers, these two technologies have become the heart of the quantum revolution we are hearing today. So we are delighted to have joined by Dr. Darius Shiri. He's our expert from our Singapore office. He has predominantly worked on quantum EDAs, and he comes with tons of research background. He's worked with Chalmers University, the University of Waterloo, and he will walk us today through all the challenges, solution in designing cell resonator-based qubits, EM core design, and cryogenic noise modeling. So he's going to talk about all of that today. And we are also honored to welcome Professor Amlan Chakrabarti from the University of Calcutta. I think everybody recognizes his name. He's been a pioneer in country's quantum research today. Anything on the quantum technology, he's been pioneering that research in India. So welcome, Dr. Chaudhary. And we also have one of his research scholars, Mr. Uday. Uday will be showcasing some of his research work that he has done to develop a 10 qubit design using Keysight ADS Quantum Pro. So he will be talking about some of the practical challenges he faced and what was there. So I think it promises to be an engaging and an insightful session. Without further ado, I would let Darush take over from here. Thank you, Darush.
Thank you very much, Shara. Thank you, everyone, for organizing this event. I'm humbled and excited to be here. So let me share my screen and then I share my slides. And please feel free to shout if you have questions, so because I don't see the chat while I am presenting. So let me share. Do you see the first slide? Hello?
Yes, Darush, please go ahead.
Yes. Okay. Yeah, this initial talk is a quick review of the features and capabilities of Quantum Pro and which is a tool inside Keysight ADS simulator, specifically for superconducting qubit processor design. And basically, the agenda is mentioning what are the challenges and how Keysight Pro has provided solutions for those challenges. So we know that there are three major components building a quantum computer. So at the very bottom of the dilution fridge, or the core of the research, or like basically the core is the superconducting quantum processor chips, and developed by different research labs and companies around the world. And here we see an example like Sycamore from Google and IBM Quantum. And then the next thing, like quantum amplifiers, we have different flavors of quantum amplifiers because they are necessary in order to increase the signal to noise ratio or increase the fidelity of reading the qubits. And in this picture, you will see the single Josephson junction-based and also the squid-based squid-based traveling wave parametric amplifier. And of course, the classical part of the design, which is also important, we cannot ignore it, is all those cables, attenuators, filters, and basically the different stages of dilution which are necessary. And we are hoping that we can also add that to the simulator. And basically, if I want to divide the design challenges, or the simple question is that why design is not equal to experiment. So one of the most important thing is that the cycle of test and developing a qubit chip is very long and is costly. And so it's better that to make this cycle shorter or to avoid error or like design not equal to the experiment. And complexity, of course, increases by the number of qubits. Superconductivity adds extra challenges to the predictability of design. For example, I have intuition. If you ask me, if you give me a piece of metal, ask me at what frequency, what happens to current distribution. But if superconductivity comes into the picture, the intuition becomes a bit difficult. And also, Josephson junction-based circuits are strongly nonlinear, and the traditional techniques like AC analysis and S-parameter analysis are not sufficient. We have to learn another set of skills. And there are also different levels of abstraction. Some people talk about Hamiltonian, they speak Hamiltonian. Then we have circuit level, we have layout level, package level, and of course, connecting everything to classical microwave. And then we have a big system analysis also becomes necessary. And on the social part, is like microwave engineers, electronic engineers, they face a huge barrier when they want enter the superconductivity and quantum computing. I blame one thing, because superconducting and quantum computing involves a lot of lengthy derivations, and then we don't have that time and patience to learn it from the very beginning by based on those lengthy derivations and Schrödinger equation and things like that. And then also quantum physicists, all of quantum physics, all of them, or most of them must not have necessarily the background or methodology of electronic design automation, like the way that chip is designed, like in classical way, like CMOS chips. So we are happy that at Keysight we have a collection of colleagues and who speak both languages, like we speak harmonic balance, we speak Lagrangian, Hamiltonian, and we are reducing this barrier. And we are hoping, we are trying to also reduce this barrier for our customers and help them to embark in this journey. And the great news is that we developed, based on our previous long experience in engineering excellence in electronic design automation tools, we developed this quantum EDA solution with collaboration of quantum physicists in our group. So we have Quantum Layout, Quantum Pro, and which is based on EM Pro, RF Pro, and quantum circuit simulation, which in which you can just treat quantum circuits as if they are like classical resistor and inductor and amplifier and things like that, and simulate. So these three bundles, which sometimes I call it Quantum Pro sloppily, but I mean these three bundles together, they promise like continuous workflow, seamless workflow. And I want to show you here what that workflow means. Like in my previous job, for example, if I wanted to start designing quantum circuits, so I have to use pencil and paper, my own code, calculate, okay, this is my qubit, this is my resonator, how much is qubit frequency, resonator frequency, what are the parameters, and things like that. And then creating the layout either manually or by code, or like Qiskit or LEDit or K layout or whatever, and drawing a layout, and then importing the layout as GDS, DXF into some simulator, whether it is COMSOL, ANSYS, HFSS, or whatever. Do the simulation, and if something is wrong or I have to change or update the layout, then I have to go back from scratch and repeat the things again. Here, with these three bundle, which I call it Quantum Pro, we just reduce this basically cycle. We made a uniform integrated cycle that you start from a schematic on the top. Let me see if I can use laser pointer. So on the top right, you start from a schematic. You just as if you are designing a from the like the panel library panel that you have in the schematic design. You just put these elements together, which I will show you shortly. And then you just press a button, convert everything to layout, and then the layout is ready. You just attach some ports to tell the layout that I want to simulate the layout, and I want to simulate and add, inject microwave signals, and then you have this electromagnetic simulation setup ready. You open Quantum Pro. This yellow layout shows what is seen, what can be seen in Quantum Pro, and then you run the simulator, either is method of moment finite element, and then after that, even instead of extracting S parameters and taking it to your own MATLAB or Python code, and then figuring out which parameter is which, how qubit resonator coupling is calculated, how this capacitor, that capacitor, everything here, just by pressing a button, you can extract this table and see the most important parameters. And from that, the rest, extracting the rest of parameters is easy. And if something needs to be updated, just feel free to repeat the loop easily, because it's just, you need to update something, a schematic, and then update the layout easily. So also at the very beginning, you can also design your qubit. You will see in this picture in the schematic, we have a library of quantum devices based on Josephson junction, RF squid, DC squid, and different connection of Josephson junction, which are basically nothing but a nonlinear inductor, but in different, it comes in different flavors. In this picture, you will see we have a loop that in one arm there is a big junction, in one arm there are n smaller junctions. You can decide n to be 10, and then bias this loop by half of the quantum of the flux. Here is shown by 0.5 volts, but this is not a voltage source. It's just emulating the black box of this fluxonium. You add a capacitor, you call it fluxonium, and then you just do the Hamiltonian analysis instead of going and running Schrödinger equation for yourself, diagonalizing and things like that. So everything here, then it will, this window will pop up. You will see the potential, magnetic potential landscape and energy, eigen energy levels and eigen wave functions or eigen states. And from the difference between the energy of the very first two states, you decide if your qubit has the right frequency or you want to update it or change it. And at the bottom, you will see the symbolic shape of the Hamiltonian, and you know which parameter affects on which part of the Hamiltonian if you want to tune the things. And also, you can treat the qubit as a just a port, RLC port, and from this port, you look at other parts of the circuit. You look how the impedance or admittance looks like from the real part of it. For example, admittance at the qubit frequency, you can extract the lifetime of the qubit, which is nothing but RC lifetime of the qubit. And this is based on a method called black box quantization, which is implemented here. So this kind of simulation is also possible. And then, of course, this is very life-saving when you can directly create a schematic and link it to a layout and update your schematic and immediately see the layout is updated. So we have this shows that, for example, especially when the chip is big, the number of qubits and resonator are large, and then you have, like, even in the cases you have 3-stack or 2-stack quantum chip, you know that how that handling that would be difficult if you want to switch between different tools. And in layout part, we have also quantum artwork, all nuts and bolts of the like a layout of the superconducting quantum chip, including qubits, and also the parts which are necessary for parametric amplifier. You will see that different flavors of qubits are here, like pocket transmon, cross-shaped transmon, different shapes of the like bends and capacitors and things like that. And even in panel number 3, you will see that, for example, one of our customers was interested to have a parametric amplifier that in which each 8-unit cell is loaded by a lumped LC filter, and we help them to add this like over the bends and also other areas. So that means that even if there is something that you don't see it in our library, we can create it for you, and it can be used by you and other customers as well. And this is the shape of the traveling wave parametric amplifier, in which the meandering nonlinear transmission line made of Josephson junction is loaded at each 8-unit cell by that LC resonator. And then when you of course started to design the layout similar to the like traditional like CMOS chip design, you have to define the technology file. We added two generic technology. One is quantum technology, multi-layer technology. And when you do that, when you want to start a workspace, I will show you later, then you can define these layers, material properties, the thickness, and even during the simulation, you can switch between metal and superconductor with given London penetration depths to include, for example, kinetic inductance, which I show you later. And one of the techniques that to scale up the number of qubits, you will see here in one of the works at Chalmers University, you will see it's like a stacking multi-chips and to be able to ease the routing and avoid crosstalk and things like that. So here we have provided multi-stack technologies, and when you, from the very beginning, you can decide if your chip has 3 stack or like 2, and so on. And this shows a cartoon that, for example, I draw a line coupled to a resonator. End of the resonator goes to the second chip by a bump, and then the rest of the elements belong to the second chip. And when you convert it to the layout, you will see that the layout, the black one, is like showing that which element is on first chip and which element is on the second chip, based on their color. And then you can convert it to EM setup in Quantum Pro and attach the signals and do the simulation, electromagnetic simulation, to extract the properties. And this is the bird's eye view of the chip. There are basically 2 flavors here. We have method of moment. At the very bottom left, you will see that this method is like less precise, but it is fast. It helps you to get the ballpark numbers. And then you go to the more expensive method, finite elements. You have better, finer meshing, and then precision is higher. Of course, you need higher memory, and it takes time, but both are available. And after that, you can just press a button, extract parameters, like the important parameters of frequency of qubit resonator, the coupling, the unharmonicity of qubit, and then unharmonicity of resonator, and the coupling between qubit and resonator, which is hidden in crosscurve or the dispersive shift of the resonator frequency as a result of qubit state. But from that, you can extract coupling. From the coupling, you can extract capacitor. And also the lifetime of the qubit here is shown, but this is due to the, for example, loss tangent that you gave to the substrate. And you can also look at the field patterns, and and the most important thing is that after you have done with the simulation, electromagnetic simulation of one part of your layout, you can extract it as a black box. The extracted black box has all information of the circuit in the layout, like the parasitics, everything. So then this can be used in higher hierarchy in simulation. Let's say this part of the circuit is part of your amplifier or part of your complex circuit what you have, and then you want to attach these to other elements. And so instead of simulating the whole circuit, you can just attach one part which is important, do the simulation, extract this black box, and then attach this black box to other elements and do the simulation like in higher hierarchy. That is very helpful. And inside this black box, you will see just ports and then abstract element, which is replacing the Josephson junction, and the rest are just S parameters based on the simulation. And even you are able to just detach this, put the real model, like the real mathematical black box model of the Josephson junction, and then play with the power and see if, for example, if the resonator based on this Josephson junction and parallel capacitor, how it behaves as a function of power using harmonic balance simulator, which is a nonlinear circuit simulator, and is one of the and it shows how the resonator, it goes to the verge of like chaotic behavior and so on. This is one example. And you can, in the simulator, you can switch between perfect conductor and superconductor to include the kinetic inductance. And that kinetic inductance, as you know, is due to the laziness of Cooper pairs or electrons who are paired in the superconductor. And that laziness means that when you ramp up the voltage, the current has delay, and that can be manifested as an extra inductance. That extra inductance is useful when you design a delay line or you want to design a nonlinear, because the kinetic inductance is also nonlinear, is a function of the bias current. So you can use it in parametric amplification. And also you can sweep parameters, just click on one component. In this picture is a resonator. You just click, you will see the list of all elements, and then you just rename one of the parameters, which is the length, which is the, I don't know what is this, length, or maybe the length of the resonator, and then you can sweep it and see its effect on the resonance frequencies, which is shown in this picture. So the sweep also is possible. And also we added flux quantization by this abstract way of introducing it in every superconducting loop, the flux which should satisfy this equation. So in time domain, it is easy because these guys are just a mathematical model in time domain, but in frequency domain is also, we managed to add this. And this is a collaboration with Google. They wanted some kind of nonlinear inductance which behaves this way. The inductance is changing this way with the external magnetic flux. So they wanted an element to simulate this. So we created this element or black box for them, and also the layout elements, and they implemented an amplifier based on this nonlinear inductance, which they call a snake. And the result of the collaboration is in this paper. And also, we collaborated with MIT to implement the amplifier, parametric amplifier. You will see here just the shape of the one. These are Josephson junctions, and then these are parallel capacitors. This is a nonlinear transmission line, or CPW, and the result of simulation and experiment, you will see here. Red is simulation, blue is the measurement, and they match. And also, in my previous research at Chalmers University, I used the harmonic balance method at Keysight in Keysight ADS, and we also studied pump power depletion and other nonlinear effects, and it was almost impossible to do it with other tools or any simulator. So harmonic balance was very helpful to get basically matched results with experiment. And the results are in these papers like IEEE Microwave Magazine, and also this paper by my colleague, which was a collaboration with MIT. And I just skipped the harmonic balance method, how it works, so you can, my colleagues have created a lot of documents. So it's a method, is an old method, but is one of the best implementation is in Keysight ADS, and it's very useful for design of nonlinear circuits. And you can make things automatic by just creating a Python code or whatever you have done, or importing a Python code from somewhere, make things automatic. For this, also my colleagues have created help. You can search API Python console and Keysight ADS, and YouTube videos of my colleague Anurag Bahargava will show up, and it is very useful and clear. In version 2026, we added early access. We gave early access for current customers. We added dilution-free, basically system model. You can just drag and drop dilution-free model here, and then define the attenuation and temperature of each stage. And from that, you can, and of course, the impedance or impedance mismatch of each stage. And from that, you can calculate how much noise will go to the very end, bottom of the fridge, and how much will be the equivalent temperature of Qubit, as you see in this picture. And then you can decide which stage is mostly responsible for this temperature of Qubit. We are adding other, like the other part of the line, which is the readout line, and is going from bottom to top. That we are also adding that in future version to include amplifiers and calculate noise figures and things like that. Also, our colleagues added the density matrix equation. The time dynamics of the qubit can be also calculated. Once you know the qubit properties, you can just enter it in a table, tell the simulator how many levels of the qubit you want to be simulated, or how many levels of resonator to simulate the, for example, leakage of the qubit energy. Or you can emulate experiments experiments like T1 experiments, measuring the lifetime of qubit, Rabi-Ramsey experiment, and things like that. And of course, you can then visualize to see what is happening to the qubit. And yeah, if you have more detailed questions, so we will be happy to provide you more documents. Email me or email our colleagues. And also our colleague Anurag Bhargava has very, very nice tutorials on YouTube. You can watch if you are not familiar with like a classical circuit design, RF microwave in ADS, or just, and also how to link ADS and Python to make things easier. And with that, I would like to thank you. If there is no question, we can go to some like a demo.
If the audience would like to ask some question, you can simply raise the hand, which you see on top of the page. Yeah. Darish, we have a question from Mr. Sanjay.
Yes.
Mr. Sanjay, you can go ahead, unmute yourself, and you can ask the question.
Yeah, I just have a simple question about the typical hardware requirement for running the software. Can you just tell us?
Yeah, like the example that I'm going to show you today is like 4 qubits. And like my laptop is like has 16 gig RAM, and one section of the simulation is manageable, but for other section is like it seems like the finite element is good to have like 32 gig RAM. So if you have a laptop or a desktop with 32 gigabit RAM, I think the reasonable chunks of your circuit can be simulated in reasonable time, like half an hour, 20 minutes, and things like that, or 1 hour, something like that. If you are talking about like 4 or 5 qubits and things like that, but I don't recommend like simulating a huge chip like at the very beginning without characterizing different chunks of that to make sure that like the parameters are what you want. And also, if you have a very big chip, it's also possible to just run it on clusters or workstations if you have access.
Okay, okay. And that's about the RAM and the typical storage requirement. What will be the typical data size that is typically, let's say, 5 qubit simulation of a 5 qubit circuit design, the kind of data, how much data does it generate? Or so that
I see. The 4 qubit that I simulated, for example, it's 1 gig or 1 point something gig, because I saved mesh and also the fields and things like that. If you save electric fields like magnetic fields and then of course you store like
okay.
So 1 gigabit, 2 gigabit.
So your typical workstation can handle with reasonable configuration of the hardware can handle.
Yes.
Okay.
Yeah.
Okay. Thank you.
You're welcome.
So if anyone has any further questions, you can write that in the Q&A chat box on top, or just the standard chat window, or maybe just raise your hand. We will unmute you and you can ask your question. There are no further questions, Dariush. You may proceed. Oh, sorry, there is one question. There is one question in the chat window. It says, do we have quantum phase slips, Josephson junctions too?
No, we don't have that. We can create if a customer wants, if it's like an existing customer, for example. So once we have cases that, for example, we work with, as I showed you with Google, for example, or it was our customer, but then during the collaboration or working with us, they realized that they need this kind of black box of inductance called a snake, and then we created that for them. So like slip phase, yeah, we have if we collaborate, work together, if you become our existing customer, then we can decide that if its black box can be created, or you can also explore, see if we have something called symbolically defined devices. Even some customers, they can independently use that symbolically defined device block, write their own equations and create a black box which simulates whatever they want. Like, for example, 2 years ago or 3 years ago, Keysight did not provide a Josephson junction model. So in my research, I just used symbolically defined device in Keysight ADS, wrote the Josephson equations, and created my own JJ and SQUID black box. So in principle, it is possible in different ways. Either we can help you, or you can also you can also do that yourself. Okay.
Sure. Thanks, Dariush. We have another question around the system specifications, but this time the question is, how many qubits can you design using an ordinary laptop? How many can you simulate?
I pushed my laptop, which has 16 gig with 5 qubit, but 5 qubit, if you want to do finite elements, my 16 gigabit laptop cannot handle that. If I want to use fine elements with refined mesh, I have to use 32 gigabyte. Sorry.
Thanks, Dariush. You may proceed now.
Thank you. Okay, so let me close this. Okay, let us start from like I just opened my key advanced design system 2025 update 2 or version 2. There's a question or about cloud, you ask about cloud platform. I have to ask, I'm not sure if it is available in cloud. I don't know. Okay, well, for the very first time when you open an advanced design system, ADS, it asks you if you have already workspace, or you want to have new workspace, open a workspace, and so on. So I just press new workspace, pretend that I want to create a new workspace. I call it delete after this. Underline work in the past that I have, and then I create workspace. And it asked me what is the technology. Is it PCB technology, other standard ADS layers for microwave circuit, or quantum technology? I say it is quantum technology library. Everyone can see that?
We're able to see your screen.
Okay, then I press next, and you will see that there are 3 options: single layer technology, multi-layer technology, Coaxmon technology. Coaxmon technology is something similar to the RICAN design, or I don't know, maybe Oxford University, Peter Lick's group, that they were designing something like that using coaxial cable to read qubits. So I just choose single layer technology. If you have multi-layer technology, you can here select it, and then let's say you want to do flip chip, you just make it 2, and you go ahead. The first set of your basically 2-tier cake or layer is this. If you hover over any layer name, you will see the thickness, you will see the material property. You can change the material property. It's like dielectric, semiconductor, superconductor, and also surface roughness. If it matters for you here, you can just fill this form and then close it, and then change the thickness or height. And then, yeah, and let's pretend we are okay. We go to the next. Next one is a second set of the layer, basically is a top chip. If it is flip chip, I just click here to flip it downwards, face, so that this orange aluminum or metal, whatever it is, facing the metal of the bottom chip. And then I go and then define the diameter of the vias connecting 2 chips together. And after that, I press finish, and it's done. But I don't want that now. I just go back without pressing finish, go back, and then I select single layer, say next, and I just assume that I'm happy with 750 micron silicon, 200 nanometer aluminum on top of that, and so on. Then finish. And it wants me to this, no later. And after I do that, you will see that under the workspace path, there is something called tech substrate. It shows just the multi-layer cake that, or layer that I created here. And yeah, I don't know what laptop is doing. Why? Yeah. And I click on this because this is important. When you click on this, it shows you all layer properties. You are able to change them here. But there is one useful tool here called Control Impedance Line Designer. If you want to decide from the very beginning, let's say you want to design the resonator, feed lines, Purcell filter, you want to have 50 ohm line. And also you need to know the capacitance and inductance per unit length of your CPW technology. So it's good to press this and you will see this line designer opens. And in line designer, you just say that I want a conductor on the silicon, and then at the bottom, I want none. At the top, I want none. So it's just a conductor. I want it to be coplanar. Oh, when I select coplanar, let me make it bigger. I press this to be bigger. So I want a coplanar waveguide on silicon. So I select conductor. At the bottom and top, I don't want anything. So this is this yellow is cross section of the CPW. The center line is number 1, and then ground edges are shown here. So I go to this table, I just select 10 gigahertz, and then I select length. Length does not matter, but let's say 100 micrometer. Then I select 12, and then 12. Then at width and clearance are the properties of CPW. I just press run. And then I want to extract the electric properties of CPW. This is the very beginning. Then you will see that, okay, the impedance, characteristic impedance is 58 ohm. Effective dielectric constant is 6 point these. These are important because it helps you to decide about the length of the resonators and things like that. And also in RLCG, we'll see that the capacitance per unit length is this much picofarad per meter. That helps you to calculate the total capacitance of the resonator, and also capacitance of transmon. If you have transmon like cross-shaped transmon, approximately you can say that I have 4 legs, 4 arms of the transmon, and each one has this much picofarad per meter. So approximately I can have a ballpark number of the capacitance of my cross-shaped transmons, and this is inductance per unit. So if you are happy with that, you can. If you are not happy with that, you just use optimize, tell the tool that I want 50 ohm, please optimize it for me, and press optimize, and then it gives you widths, which gives you exact 50 ohm. But here, I'm not concerned about 50 ohm. So let's pretend that we already designed 50 ohm, and we know these numbers. We just write it somewhere in a code or a calculator, and we proceed. Do you want to save session? You can save it. But okay, so let's open a schematic. I call the schematic for Qubit, create a schematic, and I just follow this examples that we have. It might be one of the circuits that ETH in Zurich has developed. Yeah. So you will see that on the very left, there are like library of all elements which are like simulators, even oscilloscopes, even like power electronic, passive elements, transistors, etc., etc. But we have quantum devices and quantum artwork. To create a layout immediately from the schematic, you have like this artwork, and you start from, for example, this. This is the launching pad, which you attach wire bond, which is basically the only place that you can connect your chip to the outside world. And then I have pieces of CPW line, and then I have capacitors, pocket transmons, etc. So let me bring one capacitor, interdigitated capacitor. I just put it here. These ends just snap on each other, but you can also draw a line if you want. Just press line and then draw the line. And then I bring a pocket transmon. I want to connect it to this line. And then for this one, I just follow the example in order to just make it hopefully faster to get some interdigitated cap finger widths. No, finger widths was just 5. Yeah, interdigitated cap is 50. Finger end gap was 50. This is just, and you have this element here, which is basically a Josephson junction is supposed to sit here, and then you have these 2 islands of metal. If you don't know what is that or what are the parameters, just click, and then you will see that its shape here appears, and there are like these pads on the, like if you hover on them, you will see the color is changing. So I want to like choose this one. I want that one. I don't want this one. I just say no. And then when I say okay, you will see that 2 of them are, like 3 of them are here, but the other one disappear. And I need a resonator to connect this qubit to the other qubit. I just put another one and then copy paste this one, put it here. And for this one, I have to change it. I don't want these pads which are like shown here on the right. So I just disable bottom right and then disable top right and then enable bottom left. Yes, and okay. And then this qubit is connected by another resonator. Press Ctrl R and then press Ctrl R, press Ctrl R and put another resonator here. I need another qubit sitting here and another qubit probably sitting here and connected to this one. Just press this so that I see the whole layout. If you want to zoom in some area, just select and zoom. So it doesn't matter the like beauty at the very beginning, but okay. What else I need? This qubit is going to this part, and then this is part, but this one needs another line according to the layout bottom right. I need that. I say yes, so I need that. For this one, I just select Ctrl C, Ctrl V, Ctrl R. I rotate it and attach it to this. This is the basically output line, input and output port. And then this one does not need the top left. No. Okay, so I have this and this and this. So hopefully everything is in its place. And this is the same. So I click on the pad. The trace width is 10. Trace gap is 10. Pad gap is 30 micron. Okay. So if you are not sure what all of this means, you can just press help and then the help page opens. It shows you the layout, how many layers are there, the color, and also the definition and default value of these parameters, and also what are those parameters like pad length, pad width, pad gap, trace width, trace gap, and so on. So yeah, this is the way of finding out. And let's go. Okay, let's go and adjust the. Let me make sure this is 3 and then this is 50, this is 50, okay, okay. And I need to do one thing more to add the like abstract model of Josephson junctions. So I just bring one inductor here. This inductor, I just click it here, just snaps here, and then don't worry about its value. You can change its value depending on the qubit frequency that you want in the layout. And what else we need? Sometimes, okay, we need ports, of course, to connect our circuit to the outside world. To do that, we just have P1, Control Z, sorry. Let me, P1, these are the, basically you define at which parts of the circuit like this is the way of connecting basically your circuit to layout, and also telling the tool later that where are you going to add RF microwave signal. So let me press Ctrl R to rotate it so that I put it here and then rotate. I want to see P1 and P2. You will see this is the edge of the, this part is edge of the, basically the bonding pad, and this part is going to be the edge of the ground, and in between this metal is edged and silicon is exposed. Sometimes you need to simulate the, for example, the coupling of the qubit to resonator, when coupling of qubit or resonator to feed line, when the feed line is connected to 50 ohm to the outside world. To that, you just need to use R space or resistor space. Yes, resistor space. This is just an artwork, is not a like a resistor in this schematic, but it tells the layout editor that I want you, it tells the simulator later that put something in between and make it 50 ohms so that it emulates the connection of this transmission line or feed line to 50 ohm word. And since I tell that this gap or this enclosure is like about 30 micron, so I make this like to be 30 micron. So this is necessary when you want to calculate the coupled quality factor of the qubit or whatever to 50 ohm word. But I don't do it right now. You don't need that now. So what else we need? Just check the parameters to make sure that things are okay. Top left, the gap is 15 is okay. Top right, the top right should be 15. Gap is 50 micrometer. Top left, the top left is this one. It should be higher. I make it 50 micron. Okay. Then everything else is okay. This one, top or bottom right, should be 50 to have less coupling capacitance. So the gaps are increased. I forgot to add ports here. Ctrl R. I just rotate them and then rotate them. P3, P4. And then for each qubit, for each Josephson junction, also I add this because that helps me to tell the simulator, for example, to tell the simulator that whoever is connected to P5, the port 5, please make the mesh finer and things like that. And later, I might be interested to just inject the signal from this port, looking through the eye of the qubit, what I am seeing, what kind of impedance or S parameter I am seeing. And from that, I can extract the lifetime of the qubit if need be. So then it's good that to put P5, P6. Just sequence. P6 rotate, P7 rotate, P8. By just this mouse wheel, also you can zoom in, zoom out. P9, Control R, P10. Then I Control R, rotate this P11, rotate it to be consistent so that I know that the odd numbers are top, even numbers are bottom, but it's not right. So, okay, I adjusted the gap of this one, the gap of this one, everything is default. Only the length of the resonator. This resonator on top is supposed to be W and G is 1010. We just keep it like this. We don't optimize it for 50 ohm. This is 600 micrometer. And let me see if the offset is 1600. And yeah, vertical shift was 100. What else? Bridge gap is air bridge. If you want air bridge, you tell that the distance between each air bridge should be 100 microns. So I just keep this. And then this one is 6,300 X offset, same vertical shift 100, and everything is the same. Here I just say 610, sorry, 6,100. I need launch, maybe it seems 1600 vertical shift minus 100 to be this one vertical shift bridge gap vertical shift was minus 100. I hope, but we can fix it. We can look at the layout, and if something was misplaced, we can fix it. So it's not the word. 1600. That was 1600. Okay. Okay, let's say we created that, and then we say layout. We go to layout. We say generate layout, and fix all components in layout. This is useful later if something is not right. You can fix it. Oh my God! So what I have done? Okay, it seems that offsets are not. Yeah. Let me see what. Okay, Control Z, don't worry. Maybe I gave the bad numbers as offset. Let me see if I can look at my other design. Transmission line. Yeah, I forgot 2 transmission lines here. One is 100, 100, 200. Yes. Then this is everything is okay. Vertical shift, yes. Okay. So yeah, I forgot to add these two, sorry. And then, yeah, so let me go back. Yeah. So I needed two more controls, the two more like transmission lines here. So I just close this. I add this CPW line, the same thing, 10, 10 by default, and 200 is okay. I just attach this to this one and then this one. Don't worry about those dashed lines. It's because it's so sometimes when this happens that you can just fix it. That means that already layout is created and the schematic does not understand the new thing being added. So you add this here. I had to add this, like these bends basically. Control R, yeah. Yeah, so these bands are, radius is 100 micron, is okay. 106 minus vertical shift, yeah, everything is okay. So I think I messed up the numbers, but if let's pretend that, okay, this is the layout, this is a schematic, and then we create the layout. So let me close this one and then go to the one which is already open for QED related. So this is a schematic. So the layout, I create the layout, generate layout. Layout is already there, okay. And after you do that, the layout should look like this. So I think I messed up the positive, negative numbers, but let's not waste your time fixing the numbers. So after you do that, you create the layout. You have this layout before you. Sometimes you might see that these arrows look like this, but don't worry, just click on them, just Control Z, just click on the arrows. These arrows correspond to the pins that you added. So just click on them Control R, rotate, and then click on the next one. Then you can see that the P1 is on the edge of the ground. P2 is the positive, like basically the positive part of the circuit, the source, as if you are attaching a source between these 2 points. This part is the edge of the ground. And this green layer, if you look at the left, you will see a palette that tells you what is the definition of layer and the color. This green one is called keep out. Keep out tells the layout editor that whatever is outside, whatever ground or metal you have outside the yellow, the green line should be intact, but whatever is inside will be etched away or will be subtracted from the ground. That leaves you a space for the main conductor, which is like this color. When you click on the, you see the color, the pink color is the metal. And this is also another part. And also let's say I don't like this kind of coupling. Then here you can just select conductor. If you see, I click and make sure that it is blue, the conductor, and then I come here, click this create path, and just click once, and then I can create whatever I want, provided that then by clicking on that, you will see its properties on the right side. The properties, you can decide if the end style is, for example, a square end. If the width is like, let's say 40 or something, then when you do that, you can just change the layout. You can edit the layout. And then you can also add keep out. Let's say you need keep out around it. Then you just do this extra keep out, etc. So that means that it's not, sometimes for some specific design or like Qubit, you don't need, sometimes you don't need this definition necessarily. You will be able to tweak the transmon shape for yourself, or you can ask us to do it for yourself. So for you. And yes, this was the thing. And you just inspect to make sure that there is no error or like no, of course, if there is error, it warns you during the layout, during the schematic to layout conversion, but you need to tell the simulator that how much ground you want. So once you have this full view and you are happy, you go to boundary. Boundary tells you, of course, as its name suggests, the boundary of ground. And then you click on this rectangle and draw a rectangle. Reasonably big, reasonably small, not too small so that it has some RF effects, not too big to make the simulation very long. If you are not happy, you can click on that, and then on the very edge, you just hover about it, and then you can adjust it, or you can see the X, Y, Z coordinate here, and you can adjust it here. So let's say we have done that. Let's say we are happy. Yeah. And you just save it, and after that you open Quantum Pro. Tools, Quantum Pro, I open new one because I have already another one was running before, so I just click new and Quantum Pro new test or any name, and we say okay. And since the layout is big, it takes a while, and then the layout appears. You can just do this, look at it, look at the air bridge, if you are happy or not. And you will see that at each, for example, place for Josephson junction, there is one abstract L2 like inductance element, and you can just make home, and then you might change the view, top view, edge view, whatever. And on the right panel, you will see that there are definition of nets, elements, substrate, materials, pins, and so on. Those are the things that which are important. You have to tweak them and then drop them down to help the simulator full electromagnetic analysis and energy participation analysis, basically to know your circuit input and output and give and simulate it for you. So yeah. let's and you will see that the yellow color is ground, and whatever was inside the keep out is etched ground, and then you have this conductor, which is, for example, aluminum in this example, or perfect conductor. So on the nets side, I just click on P1 because I remember that the very first thing which was attached to the edge of the ground was this P1. I right click and tell the tool that this is ground. So then P1 is ground. And then the rest of the things, P2, P4, P5, P6, etc., I can just introduce them as signal. And then components. I have like 4 components that I have to tell the component model in the full EM analysis. What are those elements? Like I just drop one of them here. Come on, drop one of them here and say that, then drop another one. It asks, do you want to create a new group? I say yes, new group, new element. And then another one, I drop new group, and then I drop another one. Yes, new group. It might be, so then I click on each one. I delete the default, which is library cell. It's just abstract, nothing there. By default, no signal will be applied there. No signal. It does not search for qubit frequency if you keep it as this. Like I just delete it. I say add lumped element and make L1 to be 11.5 nanohenry. Then make L2. So let me check with L1 to be 11.9 nanohenry, and let me check it with other things so that I don't have. L1, I don't want to mess up with qubit frequencies on L1, L2, L3, L4 to make sure that the names are the same. So L1, L2 is this one, L3 is the one, L4 is the one. Yes. So L1 is 11.5 nanohenry, and then this one remove. I make it 11 nanohenry at 10.5 nanohenry. And then the other one remove, add another one. This was 10 nanohenry, 10.5. Okay, this is done. I tell the tool that these are the components, the like abstract elements for Josephson junction, but I need to tell what are the ports. In the pins side, you can, in the top side, you have all list of the pins. Just if you click them, you will see that they are like P1, P2, P4. For me, it's important to look at S21 parameter or S11 transmission from this port to that port. I'm not going to look at each Josephson junction port. So I just click, press shift, or just press control, just P1, P2, and then P3, P4. These 4, I just drag and drop them on ports. And if you click on that afterwards, you will see what I meant by positive part or positive part or negative part. And then the other one is here. So this is where you inject the signal. For example, in ANSYS HFSS, you have to draw a line here or put a sheet here, called it, tell the simulator that I need the long port here and inject the signal from here. And then options. So let me just options. Options tells you what do you want to do. So the default is like simulate adaptive like sweep between this frequency, a start and a stop. I just say a start from 4 gigahertz to 10 gigahertz because, or maybe 11 or 12. And always meshing starts from the highest frequency based on the wavelengths of the highest frequency. I know that there are some qubit frequencies around the qubit frequencies are around 6 or 5 point something, and the resonator frequencies are around 8 gigahertz. So you can add another like linear sweep. For example, tell the tool that sweep for me from, let's say, 8 gigahertz to 10 gigahertz and 21 points or something. And in the simulator part, you say that I want momentum microwave, which is something in between momentum RF and a finite element in terms of the resource. Precision is better than momentum RF, but not as good as finite element, but it's faster. And then mesh density, let's make it 100 cell per wavelength. And inside the mesh generation, I say it is automatic, but I need to, no. Yes, mesh generation is automatic, but mesh density is 100 cell per wavelength, but some ports need a special attention. And those are the ports, like 8 ports for qubits, as you remember. So we have P9, then we have P8. Just all those 8 ports that are attached to 4 qubits. Not P1, because not P1, not P2, because those are for the circuit. P12. Those are for the input and output. Sorry, let me delete this, delete. And then I just repeat P4 and then P5. And then I go up, I just say 1000. I just Control C, keep it, Control V, Control V, Control V. But okay, it's a bit. Okay, if you want more precision, you can come here, say that I want the conductor also, the central line of all CPW line and resonators also be meshed with more precision. But here, for the sake of time, I don't do it. I just leave it. But it's possible to decide which part you want. For example, let's say in some design, you are very concerned about air bridge. You want to simulate with fine mesh over air bridge because you are investigating something. Then you can tell that, okay, do the meshing more like refined around air bridge or whatever layer is important for you. And it can be done automatically. So when you're happy with that, and then edge meshing is also suggested to be automatic, because depending on the electric field intensity, then it can refine the edges and done. And then you just press run. And it shows you this, the status, and this is the log file, what is happening. The meshing first starts from the highest frequency at 11 gigahertz. You will see that it's not yet created. It's just generating mesh at 11 gigahertz. And if you just click on this plus sign in results, you will see that you have mesh, S parameter, time domain reflectometry or time domain reflection or transmission, extracted parameters, and field, and also generate test bench and generate sub-circuit, which are very useful. So meshing is done. If I click on mesh, I can see that. Just ignore that message. Where was that? I have to ask my colleagues what is that message. So you will see the meshing is done. You just, instead of that yellow layout, now you have the mesh. So you can just inspect if you're happy with this. So if you are not happy that like this part is just 2 sections, then you can go and say, ask the tool to make this cond or conductor layer like have more refined mesh, like many rectangles instead of these like 1 and 2 triangles. And you can change the color or whatever here. And then S parameter calculation has started. You just click S parameter, you will see this window. tells you which port you are concerned with, and also this matrix of S11, S21, S22, and so on. So by just clicking on this matrix element, you can decide if you are plotting S11, S21, and so on. Let's look at S21, and you will see that only the first point has calculated. The rest are underway. So let's look at the status. Yeah, you will see the status is sweeping starts from the beginning of the range and then some points in the middle. This is the beginning of the linear range. So because of I asked some linear also sweep around 8 gigahertz. And because of that, it takes more time. But this is necessary. Since you are a designer, you know that where are your resonance frequencies. We cannot just blindly say that, okay, sweep for me from 1 gigahertz to 10 gigahertz. It's better to know based on your design what are the frequencies at least, and then guide the tool basically to help you to find those parameters. Yeah, and whenever things are being done, you will see the update. And this tool is this algorithm behind this is intelligent to extract the resonance frequencies. And these are the fitting points. Default is 1000, or simulated, you will see a terrible lot. But after things are done, you can just select 9000, 10,000, and then you will see the fitting. This is the initial fitting, but it's not yet there to find the frequencies. Or let me see if I can zoom, see if anything is going in between. So this, no, not yet, because the sweeping has just started at 8 gigahertz, the linear sweep. So yeah, let's yeah, instead of let's keep you waiting, let me see if I can just stop this. And then open. The one that I already simulated. No, this one. This. Yeah, this is the one that I already simulated. So the results are there after it took like half an hour or something to get that done, because I have 16 gigabit RAM. So after mesh, you get, of course, S parameter is finished. After S parameter is done, then I just go to view, look at like better resolution, 10,000 point. You will see how the algorithm found those resonance peaks. 4 things is happening here is because of the qubits, and 4 things are happening here, of course, because of resonators. Those points help the simulator to find them. You can just zoom to see what they are, and then you can use marker just to put the marker, where is marker? To put a marker and see if the numbers make sense or not, depending on the length of the resonators, or like the capacitors or the design of the qubit. So this is what you can do. You can extract it as a CSV, take it somewhere else, plot it, and reprocess it. But then after this is done, you can just press extracted parameters. When you say extract parameters, you can see the qubit 1, 2, 3, 4, resonator 1, 2, 3, 4. And you can see the resonance frequencies of each. The list of inductances are also given. And then the green terms, the diagonal terms in this basically general matrix, are unharmonicities of the qubits, and then unharmonicities of the resonator, because resonator is also coupled to a nonlinear word. and also its resonance frequency depends on the number of photons, and this is the reason of the unharmonicity for these guys. And then from these green terms, you can extract the capacitance of the qubits. And then you will see that between each resonator and the qubit, like there is term called chi or cross-kerr. Cross-kerr is basically calculated from this green and blue term. And from that, you can extract the qubit coupling, qubit resonator coupling strength or coupling capacitor from these numbers. And when you see R1 and Q1 here, you see empty box. That empty box means that R1 is very far from Q1. So that's why there is no interaction. Yeah. And after this is done, you go to more precision method, energy participation analysis. That gives you the quality factor of the resonator and qubit and also the lifetime. For that one, energy participation analysis, you don't need to do anything. Look at this just menu here. You only need to just drag all those components, all those component models, inductors, just drag them and drop them over component models here under energy participation analysis. When you do this, then all those components are here, except options is different. When you click on options, in options, you say a start frequency, a stop frequency, and how many eigenmodes you want. You ask the tool to find 8 eigenmodes between 4 gigahertz and 10 gigahertz. If sometimes tool warns you that there is more than 8 eigenmodes, but those eigenmodes might be due to other things like a slot modes or maybe chip mode or maybe mode of the feed line, the resonance mode of the feed line. But since I am sure that I have 4 qubits, I have 4 resonators, so I want to ask the tool to find 8 modes here. And I save fields here, which of course that takes memory. And in advanced options, I don't need to do anything except that mesh size is automatic, except the conductor. Over here, I click on edit and tell that for conductor or those purple lines, just make it 10 micrometer or 5 micrometer, half of the width. Is suggested to be half of the width. And if I select, I do that, then I'm done, and then done, and then I can run this and get more precise results like finite element mesh extracted parameters and also the field. And all of that is based on calculation of based on the finer results, and the results are more precise compared to this ballpark table here. That one takes like a lot on 16 gig RAM but if you have 32, it takes like 20-30 minutes-ish. I have that. Let me see where it is. Advanced design, qubits work. 4 qubit chip, Quantum Pro. Yeah, after you do that simulation, this is the, sorry, let me show you. Let me just unload everything. After you have done that energy participation analysis, the second simulation, you just come to results and click on mesh. Mesh can be observed here. You will see that it is a very fine mesh. It's very good mesh, no issues. And then you click extracted parameters. This table will appear, and this is all kind of couplings between even if a resonator and qubit are not supposed to be coupled, but the coupling value is calculated, and you will see these very small numbers are the very are for those which are not coupled together, but this is due to crosstalk, due to stray electric field, magnetic field, and things like that. So that is useful to characterize how good is your layout, if the chips, if the resonators should be far apart, or which part is causing more crosstalk, and if it is an issue or not. And you will see more precise numbers. Instead of 300, you have right now 288 megahertz, 285 megahertz, and so on. let me see yeah. So then you say, okay, what are those, what I can do with this number? So either as a designer, you can initially design, start from these numbers and design your chip, or from here, from this analysis, you know that alpha R and harmonicity of resonator are given, and harmonicity of the qubit is given. So chi is, sorry, happened. Okay, chi is twice of that. Sorry, there is a mistake here. 2 times the square root of this. From chi, you know the equation of chi, or crosshair or dispersive shift. From chi, you know that chi is equal to this thing, g squared on harmonicity of qubit over the detuning, the frequency difference between qubit and resonator. So you know all these numbers. From that, you can extract g. How much is g? And from g, you can extract the capacitance of the qubit coupling capacitance, Cg, because in this equation, you have everything except Cg. CQ is qubit frequency. You can calculate it from this equation because unharmonicity is given by you, are those green numbers in the table. Resonator has capacitance. The capacitance is total physical capacitance divided by 2. The reason is in the Posar's electron microwave book, or I have an application note which we can share with you why this is that. What is this total capacitance? The total capacitance is that picofarad per meter, which we calculated at the very beginning, times the full total length of the resonator. From this, you extract Cg, and then it's better to, initially, it's better to just start from this. Instead of jumping into a big chip, just design a single chip, characterize it, sweep these parameters like this, for example, length of the resonator, or this claw-shaped, or length, or gap, and things like that, and have a bunch of plots and fit equations for yourself as a designer. For example, if you are CMOS chip designer and you are given a new technology, let's say FinFET technology, 7 nanometer channel length, so you have to have a bunch of simulator in Cadence, simulate your transistor bias, calculate IV characteristic, transconductance versus, for example, width of the transistor versus gate length of the transistor, etc., etc. And those plots gives you basically are your design library, and from that you can start design a bias and amplifier, etc. So here also you have to have that kind of attitude. So just sweep different things which are important, have plots and fit equations, and from those your own fit equations, you know that if you make this claw narrower or bigger, how much would be the capacitance, coupling capacitance? Is it 5 femtofarad or like 10 femtofarad, etc. So such that when you look at a layout by naked eye, you can have an idea how much is this capacitance here, how much is this capacitance of this transmon, etc. So that you don't need to over simulate things, because time really matters. After you have done that, after you have done this characteristic, you have your own personal library. Then you can write code snippet or calculator, or you can use this. There is a website, Transmon Qubit Calculator, by Anton Potoshnik from IMEC Belgium. So he has done a good job of calculating important things. You just insert the numbers and then get the parameters, start your design at the very beginning of your design, or you can write these equations for yourself and have them. And then fill this table, like saying that resonators, I want detuning to be 1.2 gigahertz. I want resonators to be this, qubits to be this. From that, you get resonator length. You get meandering length, the real meandering part, because there are some hanging things to the resonator, you have to deduct them. And then charging energy, shunt capacitance. From that, you know the size because you have done simulation. Then from that, calculate Josephson energy, and then Josephson energy divided by charging energy. You should make sure it's a big number, because otherwise qubit will be very sensitive to noise, charge noise. And then coupling capacitors, you decide how much you want, or either way. You decide from design G and then calculate this. And yeah, and then you have this basically library for yourself. So it's up to you to decide which way. Yeah, these were the, yeah, I thought that in case simulation does not work, these are the numbers. Okay, after this thing is done, the finite element is done, then you can look at the field. You just click near field, and electric field is loaded. Let me just unload pause and start again to see it in a better shape, because it was overlaid on the mesh. So here you have list of those 8 frequencies, qubit frequencies and resonator frequency. You can just switch and look at the resonance pattern. Like, since this is Landover, since this is half wavelength resonator, so there is a notch at the center. Voltage is minimum and then maximum on both ends to couple to qubit. If you want to see qubit frequency resonance, you can look at it here, and so on. So I don't have anything to say more, but if there is question, just please. I hope I could show you a glimpse of what is happening or how the design is. Yeah, there were some glitches. Sorry for that, but it happens always. Yeah.
That was very insightful. Thank you very much. We have a lot of questions. Maybe we will park the question towards the end, because we have some exciting things to be shared from Professor Amlan and his student.
Yes. Yeah.
So, yeah.
So I stop sharing. Yeah.
Yes. Professor Amlan, can you hear us?
Okay. Yeah, I can. Yeah, I can hear. I can hear you. Yeah.
Good afternoon, sir. Thank you for joining us.
Yeah.
And sir, I think before we did give an introduction about you. I know you've been pioneering this research of quantum. Everybody in India, when we talk about quantum, the first, in the academic field that comes up is your name. So thank you for joining our session today, sir. And I will let you take over from here. Thank you.
Yeah, thank you. Yeah, thank you, Keysight Technologies, and and thanks to organize this workshop. A fantastic presentation by Darush. Okay, I thank you again.
Thank you
for taking this journey on the quantum media platform. That means of Keysight. Actually, yeah. So academic journey in quantum is long, but on this quantum media of Keysight, we are also experiencing the tool, and I think for the last 3 months plus, we are working very closely with the team of Keysight, right, and trying to develop something in our lab, which my student Uday will demonstrate just after my brief discussion. So what I will present today is obviously Darush has presented the key thing, that how we will try to generate the qubit design. It's very important that let me start sharing my presentation and again that means and again discuss with you. So fine. So the basic motivation here is that we want to design the qubits, right? And it's very important, because though we know that presently we are heavily working on quantum algorithms might be, and we are working on the quantum physics also, but what we want to do at some point of time is that we have to design our own qubit hardware. Okay, can you just give me the permission to share my screen? Yeah, the organizers, I think.
You can just share, click the button on the top right. You will see a share option. You can go ahead, sir. You're already a presenter.
I'm sharing, but somewhere I'm seeing that when I go to the entire screen sharing, the button is not enabled. I don't know why. Button, okay, let me share. Okay, can you share? Can you see my screen now?
Not yet, sir.
Is it visible?
No, not yet.
No? Okay.
No.
Okay. Let me go back. Uh, Let me go back and maybe try to share my screen.
Yes, it's coming up.
It's coming up now. Is it coming up the screen?
Something is coming up, but still not seeing your presentation. So while you set this up, Dariush, there is one question in the chat window. If you can take that up while Professor Ramlan can get these things right.
Okay, I go to chat window to see.
I think there was a technical glitch. Professor Ramlan has dropped off from the call. Dariush, I think there is a question on how to implement via bonds in the layout, especially for the CPW and the charge lines. I think you addressed this in the presentation, but if you want to take this question up.
Yeah. Yeah, we have default air bridge. We have air bridge by default in the layout generation. But if you don't, for example, like it or it's not flexible to put it where you want, after you created your layout, you can go there and manually add the bridge layer. So let me see if I can show you layout. Layout. No, this is not here. So these air bridges, the blue one, you will see that they are added by the tool itself. But if you want to add something yourself, you just let's say for some reason you need something here, so just come here. You will see conductor air bridge. Just click on that, and then just draw here. So since the thickness in the technology file, it is already defined that how high it is. This like from the layout, like in the default setting, it says that this is 8 micrometer high. So it's like a bridge, just bridging over this purple thing by like 8 micrometer over it. I hope.
Thanks, Darush.
Yeah,
Professor Amlan.
And then via air bridge is another layer. Maybe you should also draw that under that to tell that it is connected to ground. One here, one here. So whenever you need, you can do it yourself if it is not flexible.
Dariush, I think Professor Ramlan is back. So we can see your screen.
Sure.
Oh,
Maybe
great.
there is a bandwidth issue. I would request you to turn off your video camera, sir, so we could just
Okay.
see your slides.
Oh, so good.
Thank you. But otherwise, you're good to go. Thank you.
Okay. Okay. Fine. Yeah. So I hope that my screen is visible to you, my presentation, and this presentation. Okay, what is the motivation of this particular activity? What we are doing in the lab, though our quantum computing lab at University of Calcutta, which is headed by me, actually mainly started with with logic synthesis and the quantum circuit design and optimization. We also work on the generating the techniques for error correction. Involving the circuit cutting and fragmentation. We also work a lot on the quantum algorithms, optimizations, and very recently machine learning. But this is the initiative what we started on looking to the qubits and trying to right? And trying to make a full stack, which means that means, okay, how you can optimize your algorithm, right, from the high level circuits to the error correcting, okay, to the error encoded circuits rather. And then when it goes to the control, right, how we can look into the qubits, how the qubits are working for the, okay, for your algorithm and for your, okay, for the circuits what you are trying to implement on your probable quantum hardware. Then we find that this tool of Keysight, which is of pretty importance, and we formed a group, right, which is presently growing, okay, which will, where our target is to find out the design parameters of the qubits, okay, for at present superconducting qubits, and try to see what are the optimization, what are the errors, what are the control sequences we need to generate for a specific, okay, quantum circuit, and obviously which leads to quantum algorithm. Okay, so cutting it short, we will make this a very brief okay, description or right of the superconducting qubit design flow, which will be okay, after I stop, my student Uday will be presenting a small demo on what we have done, okay, using this Quantum Pro 2. Okay, so we know that, okay, what we are trying to do in the simulators, which is the Quantum Pro simulator of Keysight, it is trying to look into the physics part of the superconducting qubits, right, and trying to generate a simulation platforms, okay, which actually tries to transform the, transform the operations, the quantum operations on a physical architecture, which is the superconducting qubits. And if we look into the foundations of this, obviously quantum physics is not a new thing. Quantum physics, okay, pretty old, and a lot of okay, things started in quantum physics, and we know that the okay, the fabulous things of wave functions, superpositions, entanglements, okay, of quantum physics, okay, and obviously we know that, okay, the birth of quantum computing, okay, the birth of quantum computing started from quantum physics, and the motivation was that we need to build quantum computers to simulate the quantum physical systems, right, at the initial case, okay, and obviously then, okay, then slowly and steadily, okay, from the quantum physics, our quantum computing originated, and we had very important algorithms, which are the breakthroughs, we can say, okay, David Deutsch, okay, Log Grover, Richard Joyce, okay, Peter Shor, okay, they all came up with the algorithms which created motivation that, hey, we need to build quantum computers, right, so that there's a real need for quantum computers which can solve some complex problems in the present classical computing in a better way, right, and can be right, and we can, and what are the things we need to do, okay, to generate the scalable quantum computers architectures, okay, and there what starts of actually thinking about the quantum hardware, okay, we require, just like the classical computing hardware in the standard VLSI design is very mature nowadays, okay, from the single core systems to multi-core to SoCs and chiplets, okay, we have actually traveled a long path, and we are generating a lot of compute in a very small amount of silicon real estate. Okay, we also have to start the journey, okay, for the quantum hardware, and it's not independent of the quantum applications. So quantum applications and targeted quantum hardware, right, which gives us the scale up, right, and also the controlling the error parameters, right, will be something which we are looking forward to the next 5 to 10 years, right, and we have seen a lot of progress here has done a lot of big giants and research labs, okay, have already come up with the quantum hardwares, okay, and also the interface between the between the high performance computing and the quantum processing units. Okay, now what we like to do, as already the previous speaker has explained in a very well demonstrated way, right? Okay, the fundamental thing is that okay, we are trying to look into the superconducting qubits, right? And the fundamental of the superconducting qubits is a transmon qubit. Okay, right? What is this? Obviously, we know that okay, we can generate a sort of an Hamiltonian function using a circuit consisting of an inductor and a capacitor. Okay, and we can have a sort of energy distribution which is being uh, which is being shown here, right? If you look into here, this is a very quiet the regular energy distribution with the phase of the phase of oscillation, and that will discuss with a very classical Hamiltonian, which is of the form combining the energy of the capacitive energy and the inductive energy. Okay, but we need to generate it in a sort of a nonlinear way. Okay, the energy distribution should be nonlinear. Okay, just to have a better control and just to make it at the scale of quantum. Okay, and that's why we built the Josephson junction, right? And this is on the right. We see the Josephson junction, which is called a transmon qubit. Okay, right, which consists of a junction which is made of two aluminum. In this example is an aluminum, but we can have different substrates also. Okay, we can have different. We have the substrates like silicon over aluminum, and there are other materials also we can look forward to. Okay, for building a Josephson junction. So if you look into the figure first on the right, we will look that there is a junction inductance LJ and junction capacitance CJ, which is the intrinsic parameters of the transmon and there is a shunt capacitor which is CS. Okay, right, and this particular inductor is being defined in terms of the current flow, okay, which is being generated in this particular circuit, and the phase factor, okay, which is phi, and we can define the L in terms of the phi and I what we have in the circuit. And there is a typical structure of this, okay, in a simpler form what we show here, which is called one aluminum top electrode and the bottom electrode, okay, which are of the order of maybe a few tens of nanometers, okay, right, and there is an aluminum oxide which is of few nanometers, okay, right, and we can form this, we can fabricate this transmon qubit, okay, right, and then the modified Hamiltonian in terms of the parameters of the Josephson junction comes like this, what we see here at the bottom of this slide, okay, and what is important here is that we need to now actually design this transmon, not only a single qubit, okay, we have to work it in such a way so that the transformation on the single qubit basically the Pauli operations, so the single qubit rotation operations we can transform the state of the qubit in terms of the single rotation operations, and also we need to have the coupling between two qubits, okay, so that we can do the two qubit operation. So that's the basic operations we need to do in a basically qubit state or qubit array. So we need to design a qubit array, okay, which will be defining a few qubits, okay, and we can make this from 5 to 10 to 20 to 50, maybe hundreds like that, okay, right, at a very large scale, right, and try to design a layout of this particular transmon qubit so that we can fabricate the quantum chip out of that, okay, and in order to do this, right, obviously the quantum the quantum pro platform of Keysight, which is basically we explored the superconducting qubit design of this quantum pro, and it does a lot of simulations and estimations and measurements we can do do within this tool. And these are, as we see here, the electromagnetic design environment, the layout of superconducting qubits. We can actually generate a lot of this the frequency domains, and these are very important to generate the control sequence for this qubits, so that we can do the actual quantum transforms on the single qubits, and also the two qubits entanglement operations, right? And we need to calibrate the qubit system for the specific control operations, and for that we need to do all this frequency and eigenmode simulations. We also need to generate the circuit simulator, the transient analysis of this transform circuits, so that we can know the different corners of the design, right? And we have a lot of this. These tools also provides a Quantum Pro Python scripting, so that we can generate our designs. And there are a lot of this kinetic modeling of the tools. Right? The target is that what I think my student Uday will just demonstrate now. The target is that that means use this analysis, understand the design principles, implement that using your tool, right? And try to measure the performance, right? And try to see that what are the after the design is what are the things you need to do further to come up with a with the layout on which you can fabricate these qubits. Or on the other hand, right, what are the control signals you need to generate, for this particular array of qubits, so that you can plug it to the upper layers, right? And you can understand that if the error happens, how we will mitigate the error in these qubits. Or you can also find the actual cost of your quantum circuits, the errors, right? And what are the entire set of control signals? Because if you look into the compilers of a quantum circuit, right, the compiler will be taking your optimized quantum circuit at the one end, and will be generating the control signals targeting to the qubits at the back end. So what we need to do, we need to understand. So the first thing is that being a researcher, being an engineer, who's trying to look into quantum computing, right? This knowledge of simulation and extraction is very important, and we found it very good. And now it's over to Uday, who will be describing the simulations what we have done till now in our lab, and we are in the process of doing further complex design pretty soon. So thank you all, and now it's over to Uday. I will just close this presentation. And right over to Uday. Yeah.
Yes.
Let's carry on.
Am I audible? Am I audible to everyone?
Yes, Uday, you can go ahead.
Yes. Good afternoon, everyone. So my name is Uday. As you know, I work with research in superconducting hardware design. So today, a lot of time, we have more than 2 hour session. So I'm just going to the demonstration of Quantum Pro, and suggest a workflow that you can use to design your layout. So let me just share my screen one. So my screen is visible, right? And
Yes,
everyone
we
can
can
see. Yes. Okay.
Yes.
Dr. Siri has explained a lot of things. So I'm not going to cover that, like creating a workspace, editing that substrate, discussing different component, and these things I'll not touch because we have less time. So I'm just giving you a design example. How can you go with this roadmap and create a better layout, and how can you design your first superconducting chip, I can say. So first, what do you need to do? We need to extract the Hamiltonian of our transform. That is important. From that point, we will start our design. So just trying creating a schematic. Like you have Dr. Siri explained how to set up the workspace. I'm not going to touch that. Okay, just create a schematic here. Just giving a name. Okay, I'm taking a transform schematic. Small keyboard, yes. Okay. This is my schematic level representation of my transform Qubit. If you double click it, you can see the critical current, junction capacitance, shunt capacitance, all these parameters values. Basically, these parameters actually can help you design your qubit frequency and the harmonicity of your qubit. So just go to tools, then go to quantum tools, and go to Hamiltonian analysis. Just read the schematic. Once the schematic reading is complete, you can see the Hamiltonian from here. Yeah, this is my Hamiltonian, just simple transform Hamiltonian. This for my capacitor, and this cos phi term is coming for the Josephson junction. Okay, that nonlinear inductive nature of that junction. So we need nonlinearity to make the qubit in a two-level system. So unwanted transition should be avoided. That is exactly what we want in our qubit. Now we're gonna calculate the data. Once it is calculated, now you can see the energy levels of our qubit. You can see the wave function also here. From controlling these parameters, like if we change the critical current and other parameters, the Hamiltonian will also change. We just open, taking it, giving you a demonstration just to get 40. Yeah. Okay, fine. The tools again, quantum tools, Hamiltonian. Somehow it's visible. I don't know why. Can you someone guide me? Like I can. Yeah, basically. Just calculate again. Calculate data. You can see the modified Hamiltonian also. Read the schematic and calculate. From that, you have your qubit frequencies and harmonicity. So these values are very much important because using these values, we are going to design our qubit frequency and the values of alpha, that is an harmonicity of our qubit. Okay. So once you get those values, like you want 5 gigahertz qubit frequency to be 5 gigahertz, like a 0 to 1 first excite, 0 to 1 transition, we need 5 gigahertz microwave pulse. So then note down these values. Okay, note down these values. And Dr. Siri already showed the site. From that site, you can calculate the different parameter like the capacitance, EJ. See, although I have not used that site, I have calculated it in my like notebook. And let me demonstrate you how can you proceed from here. Okay. So once it is done, you can like search here for quantum artwork, because if I try to generate the layout of this transform qubit, so there is no quantum artwork attached to it. So if I just let me just show you a click on generate and update layout, nothing will come. Nothing will come because no layout is connected to that specific schematic. Okay, so let me create another cell. So a second. Yeah. Just I have already created a model while Dr. Siri was giving the presentation. So I'll share you the schematic of it, right? So, sorry. Okay. So this is the schematic that Dr. Siri already created. Okay. Yeah, like he has already explained there is all these ports and R space, these components and what it does. So I want to point out this capacitor. This is my capacitor that is called interdigital capacitor. So they set the external coupling rate of the resonator, which determines how fast you can read out the qubit. So from the beginning, we want to like follow a architecture, like how fast we want to read out the state of the qubit. For according to that, we'll set up these values. Like if you double click on it, there is the finger number of fingers, finger width, interdigital gap. These parameters, these things we can like modify and find out the capacitance from it. Okay. So once the layout is done, someone from the chat was asking a question about what is the nonlinearity coming from. So you can see it from here that there is a model called Q inductor abstract. This represents the Josephson junction inductance Lj. It's nonlinear, giving the qubit its enormicity. So you can have a distinct like ground level and excited level without populating to higher states, right? So once the schematic is finished, you can go for layout and I just generate generate that layout. I've already generated the layout because it will just again fix all component and like align it differently. So I'm going to the layout. So this is the layout of the transformer. Okay, so just going to Quantum Pro and in Quantum Pro. I've already simulated this because it will take a lot of time. So what I want to point out that from that Hamiltonian, you calculated the transform parameters, like these parameters, that you need to know what is the gap between those capacitive pads, what is the width of the this pad, and these things. These things control the actually affects the qubit frequency, right? So these things you need to modify according to your specific qubit frequency, because if you're working with like more 5, 10 number of qubits, so you don't want frequency crowding to be happen. So from the beginning, very beginning, we'll design our qubit frequency and their anharmonicities as per our plan. Okay, so we are just going to simulate it. Open quantum flow. I'm just clicking on this one. So for the Fullium analysis, if you see the Fullium analysis, we need to create, we have to create ports, right? We need to create these ports. Okay. But if you are going for like energy participation analysis, we don't necessarily need to create this port again. Okay. Don't need to create this code. Okay. So I'm going directly to the energy participation analysis. This is using the FEM method to solve the layout. Okay. Just click on option here. Here I am like 5 number of eigenmodes. I will set it to 5. If I click on advanced option, there is an option called target mesh size. Like if your system has low specification, what you can do, you can just click on it and set it to minimal memory. That's how you can simulate it in a like low resource system. Okay, just not doing anything because Dr. Siri already explained how to like edit the mesh, define the mesh, increase the mesh density and all those things for better results. Just running it. It will run very quickly. It will take like hardly 1 to 3 minutes. So while it's running, one thing I want to point out is that why I was interested in this ADS quantum pro solution, because the challenge of flux quantization that was solving by this tool, because in superconducting circuit, the magnetic flux is the fundamental variable. So the key principle is that the flux enclosed within any superconducting loop must be an integer multiple of the magnetic flux quantum, that is h by twice c. So most EDA simulators solve for node voltages, like if you use cadence and all, solve for node voltages and do not inherently respect this flux quantization constant. Okay, posing this is a significant challenge for designers to simulate superconducting qubits. To properly simulate loops containing inductors, the new Fluxware inductor models were introduced by Keysight. That paper sir was mentioning earlier with collaboration with Google. In that paper, like all the method has been explained. Okay, you can view that paper, read that paper. That is a good paper to understand why we need a flux quantization of all those things. So this simulation is running. While this simulation is running, I think I have run the Fulham analysis earlier. So I'm just going to results, base parameters, because yeah, I hope so. Yeah. Yes. Just- Yeah, right. So I have earlier run the Fulham analysis. So here you can find out this parameter. This is for my qubit. This is for my resonator connected to my qubit. Okay, that we can find it from here. If we click on extracted parameters, from here also you can find the qubit frequency and the resonator frequency. All those things you can find. Okay, so basically what we are doing earlier was we are making a model of our qubit that these parameters need to be changed for this specific frequency and this specific anharmonicity. So we must avoid the frequency crowding problem for larger one having more number of qubits in a single chip. Okay, so the simulation is complete. Going to results. Sorry, I'm not. Click on extracted parameters. We're saying no. So it is something is not. Sometimes this tool has some glitches. I've already run. Let me open it.
Uday,
Yes.
you forgot to add inductor in components model.
Yes.
That's why it does not.
Yes.
Go to energy participation.
Yes. Thank you. I just forgot. Here
I
I
should
need
have
to.
seen it sooner, sorry.
Yes. I have like I said another Quantum Pro setup. This is, I guess, Quantum Pro 1. I have already like set up.
Really?
Yeah. For this one.
Yeah,
No. I was simulating the wrong setup. Yeah. While you were explaining,
I was. Okay.
So what sir pointed out that you must set this lambda model. Otherwise, you can't find the qubit frequencies in if you click on extracted parameters and then go to results and click on no simulation problem. Let me run it. Wait. Okay. It will run it. While it's running, I'll try to explain few things that sir pointed out earlier. That in the Fulham analysis section, you can see if you click on results, you can see the generate subcircuit model. If we double click on it, it will like create that black box that sir was talking about earlier. Okay, from here you can like make a symbol of that black box and use it in your like ADS schematic. That you can do. Running, it will take some time. So regarding the hardware resource, like someone like early in the meeting, someone was asking about what hardware resource we need. What I have seen is like if you want to simulate 10 qubits, like if you want to see, find out, let's suppose if you want to find out 20 eigenmodes, each eigenmode will take like almost 20 GB of your memory. And you need a good RAM because if only let me just one second. Yeah. For this, Okay, I'm simulating a single qubit. You can see memory GB, how much memory it consuming. You can see it from here. Okay, from that you can calculate how much RAM you needed as per your processor and hardware. Okay, so just wait for a minute. It will run quickly.
Your qubit had 60 femtofarad capacitance. So do you decide beforehand it should be 60, or do you after simulation you realize that those patches have 60
No, no, no,
femtofarad?
no, 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 no. So actually, I am demonstrating a like test. This is not my actual work. So what I started my work with, just I start with this circuit. Then from that I find the Lagrangian, and then from Lagrangian I calculate my capacitance matrix, then Hamiltonian, then quantize it. I follow the mathematical framework first. Then I come to the layout part. Okay, like if I want to build a specific type of coupling architecture, you know, there are Gmon couplers, different type of coupling or tunable couplers. So as a researcher, what we need to do, we need to create our own coupler so it performs better. Like that kind of research we want to do. So for that, we need to go from the quantum mechanics, like math part, then map it to our layout, like as we do in analog circuit design. Right. In Cadence, what we do is like we create our circuit and then frame a mathematical model like small signal analysis model, then calculate the gain and the bandwidth, all these things, then come to our schematic and design our schematic, then go for layout design, this process. So I'm following that process of VLSI design, that process. So yeah, that I'm following, sir. It's completed, yeah. And something is wrong. I don't know why it's not showing simulation complete. Okay, okay, okay. Yeah, you can see now. You can see the qubit frequency, the resonator frequency, the qubit anharmonicity, the T1 time of my qubit, the quality factor, and everything. You can see it from here. Okay, so accordingly, you will design your qubits. Like if you making a 5 qubit layout, so you need to have five frequencies. Like if you're targeting for your qubit, you will design those using this model. Just create this model. These are already available in examples of if you, I don't know, my option is not working like after the 2026 update. So if you go here and open those examples from that model, also you can start your design, like how to find out that qubit frequency and all. And you can always go to the help section of ADS help. If I open the layout again, if we go to help, layout, Windows help, you can search for quantum. And from here also all the documentation of quantum is available. Okay, you can use that too. So once you have found out your 5 qubit frequency, like I'm like demonstrating a 5 qubit layout here. So that's why I want to find 5 qubit frequencies. Okay. Just this is complete. I have designed like I have all the parameters, these transform parameters I'm talking about. These things I have for my qubit, specific qubit. Now what we're gonna do, we're gonna follow a architecture. Like Sarah has earlier shown a 4 qubit model that the coupling was done by the bus resonator. Okay, there are different coupling methods that we can use. So coupling is very crucial for a 2 qubit gate implementation. Okay, so we need to focus on the coupling architecture of qubits. So I'm just gonna open our 5 qubit layout. So this is something we're testing. Okay, something we're testing. Yeah, the transmon other arms are disabled from here. Yeah, only taking one arms. So this is the architecture that we are testing. Okay. So again, the sir has encountered a problem that when sir go from schematic to layout, all the components are like abruptly, like randomly arranged. Okay. you can avoid that problem. Okay, you can start from the layout. You can start from the layout, and once the layout is complete, like you have this quantum ad hoc model, right? You can just click on and like drag and drop, easy. So once you have your layout, you just need to generate your schematic from it. Okay, just go to schematic, and here is the option generate slash update schematic. Click on it. Just fix all components. Click on OK. You know, still unorganized. I don't know why this is happening, but still you can go back from layout to schematic also. Okay. So this is our layout. So we're going to open Quantum Pro. Just simply click on open. Okay. So, so we need to set the ground net that I have already set, that ground port that I will show, Sarah shown earlier. Okay. So what I'm going to do, I'm not going to do Pulliam analysis, although from the Pulliam analysis also I can find out the qubit frequency, but the energy participation analysis helps me like save some time of me. Like I don't need to create ports and all those things. Okay. So just going to component models, that these you need to define. Okay, just drag and drop from it here. From here, okay, you have components. Then these inductor models, if you expand it, you have these inductor models. For each qubit, we have inductor models L1, L2, L3. This must be like just drag and drop. If you double click on it, I have created different groups. Like for middle one, just one group, and this just for first simulation. I can explain it like very quick. Okay, now next thing.
So instead of saying that each one is different group, you just group them two in one and two. That's why you have three bunch.
Okay. Yes. So just for like demonstrating. Okay.
Yes.
It will save a lot of time creating those, because you like while your presentation was going out, I was figuring out that it takes a lot of time to create from scratch, right? So it's better to let's model these things. Much. So going to simulation setup. Here I want to point out something, that once you know that what qubit frequencies you are working with, you don't need to like simulate in this plot range. I hope you can, because if you go for higher number of qubit, it is much difficult for a laptop to simulate that whole layout, right? So just always check this option if you're simulating using a low resource laptop or a hardware. Just click on advanced option, and target mesh size should be minimal memory. Should be on minimal memory. Otherwise, you need a lot of RAM to simulate this. Okay. And once you have found out, like once you have good hardware, then you can like define that mesh better for better result. Just and click on done. Not going to any technical things. And you can for faster simulation also, you can choose the max rate per job. You can set it to according to your hardware specification. Like I have a 6-core CPU with 12 threads. So accordingly, I have set it resources. So I've checked this simulation, like how can I faster simulate it? Just clicking on to run. It will take hardly 7 minutes, approximately 7 minutes it will take. Okay. So just coming to our layout while it's simulating, there are different coupling methods that you can use, that I was talking about. If you go to Qiskit Metal, from Qiskit Metal also, you can still import your layout from that to ADS. Okay, that also you can do. I have seen that. So let me demonstrate that. Just click on layout. Q Metal. I'm taking right. Yeah, Q Metal. Sorry, I was supposed to create a layout, right? Yeah. Okay. Yeah, once your layout is created, go to File, then click on Import. And from here also, you can import the GDS file generated from Qiskit Metal or any other tool that you are using. Just click on File Type and click it GDS to stream format. Just import, click on Browse, and go to, that is a pen, GDS for QCDS. Okay, fine. While it's imported all the layouts, right? You can see it from here. You click on top. Yeah, this is a 4-qubit layout, like from imported from like Qiskit Metal. Can do also. Just while simulating. So no simulation. Yeah, this one. Yes, see now you can see if you choose the minimal memory option, it will take a lot less memory to simulate this. But the mesh size, mesh definition is not good. But we can still extract some result for research purpose. Siri sir, can you now take those questions while the simulation results? Hello.
I think Uday, Daryush, he is there, but I think there is some issue with his end.
Sorry, what is the question?
Okay, just asking you to take some questions, like if you want to answer anything from the chat, because it's simulation process is going on. So sometimes.
Someone asked if, for example, they can have their own air bridge, but I was not sharing my screen. Maybe in one of your layout you can just draw an air bridge, just to answer that question.
Yes. Actually, like this meeting is like for almost 3 hours. Like we have another meeting after that. We have only like 13 minutes of time.
So don't ruin this layout. Or maybe I can at the very end I can share my screen. So don't worry.
Okay.
Okay, Uday, while your simulation is running, firstly, thank you so much for sharing this story with us. It excites us that you've been able to achieve the results that you want. And to all the attendees that are here today, like Uday, there are many researchers across the globe who've been using Quantum Pro solution of Keysight. So it's ADS Quantum Pro. We have the likes of AIST in Japan who have been using it for a very big research. We have customers like Google. Google, in fact, produced their chip. They displayed one of their chip, which was designed with ADS Quantum Pro. And likewise, we have Raytheon, Boeing, and several customers across the globe and in India as well. Several universities are using. If you also want to join that line, if you want to start researching and start using ADS, I have posted one link in the chat window. You can click on that. It's a small feedback link. You can enter your details, and if you're interested in evaluating the software, if you want a free license to be sent out to your email, just mention that in that link and we will send you. We have a partner here, InfiniPoint, who will reach out to you and arrange the licenses. So InfiniPoint is our partner for all the academic and the commercial accounts here. And they will reach out with all the licenses, the installation instructions, and if you require any further training or handholding on the software, we will be able to do that. You can reach out to Keysight or InfiniPoint at any given point of time. So it's a small request to all the audience present here to fill out the feedback form in the link. Okay, thank you.
Yeah, just to add to this, that means as I am also from academic background, I think the quantum lab, which is now every institute is trying to have the quantum lab, the quantum engineering lab, and also AICT has started a minor course on quantum. A proposed syllabus for okay, for the quantum lab. I think this okay, this type of tools are very good for the students to okay, to correlate the physics, okay, the quantum circuits, right, and the physical systems, the physical qubit systems, right. And I think this okay, this simulation is very much okay, part of the course of the lab, right. What is required to make a student capable of knowing that what is that okay, how a qubit system works. Yeah.
Thank you, sir. I appreciate that.
So we have planned many things to show today. Yeah. So the simulation is complete. Yeah. So we have planned many things to show, but you know,
The time is limited,
yes,
so we have to wrap up.
yes, yes,
Yeah?
yes, yes, yes. I know, I know, I know. So I'm just going to show the results and what we are targeting to achieve in this design. In this design, what we are targeting to achieve is that we want to see okay, the control these values, this Q1, Q these cost square values that we want according to our design, like our method from mathematics to here that we want to design because these are important for 2-qubit. So we don't have time for this to discuss today. Like how can you build a 2-qubit gate architecture without a tunable coupler, So again, any day, any other day, we're going to demonstrate that. Maybe sir will, I will hand over this to sir. Sir, what will happen next?
Yeah, fine. I think we are done. If Darush has to say anything more, okay. So I think as from our initiative, we are looking as you know that we are trying to look towards the design and simulations of the larger qubit systems, right? And also we have some plans to how to couple this qubit systems with the high level quantum circuits and try to develop some intermediate compiler, okay, which can validate the validate or at least extract certain physical parameters of the quantum circuits or the parameters of the control signals, okay, for a given quantum circuit mapped to a physical qubit system. So a lot of research problems, okay, we are trying to think, and obviously we will work with industry partners and other research collaborators in this domain. Yeah. Thank you, Uday, and thanks to Keysight for this excellent event.
Thank you. Again, we're just leaving this meeting. Sorry, thank you.
Thank you very much.
Yes, thank you,
Thank you, sir.
sir.
It was a pleasure having both of you. Thank you so much.
Thank you,
And
sir. Thank you.
Sure. Once again, Dariush, thank you very much. I think we have crossed the time. We were much over the time limit, and it's lunchtime in India. So I do not want to be holding more people here. Once again, thank you everyone for joining us for this session. Just another note, if some of you did not get a chance, if your colleagues or someone did not get a chance to attend today, we have a similar event happening on 18th. We have one of our other expert who will be presenting on that day, 18th of this month, August. You should receive the invites for that as well. So please ask your colleagues to join in, or if you could not attend the full session today, please join us on that session as well. So thanks once again. And one final request is please fill the feedback form. And if you need the license, do specifically mention that you need the license and we will reach out to you. That's it from our end. Daj, if you want to take up some questions of the people who stay back, you could do that. We will leave the chat open for the next 5 minutes.
Thank you. I don't want to keep you. Thank you very much. A few questions were asked, but we can address them offline. Or maybe like I can share quickly my screen and show the layout that I was showing. Where was the layout? Yes. Here I mentioned that, for example, if someone asked if he can draw his own air bridge, I said that if you don't like this air bridge, which is 8 micrometer above this thing, you just in the layout you can choose air bridge, conductor air bridge, and draw your own air bridge or whatever connects this part, and then the footprint of air bridge is also you need 2 pieces of metal. Just telling the layout that those footprints are attached to both grounds on both sides of the CPW or whatever you have. So if you are not happy with air bridge or their period or the size, you can design your own in the layout wherever needed. This was something, and then also try to make your designs modular. For example, when you create a layout, let's say this is a layout, just go to window, make it a symbol, and then make it like a part of your layout, make it a symbol, and then have another big hierarchy or big schematic, just import the symbol, like as if it is a circuit element, import the symbol. And then over here, it is easy to like have different layouts, different sections of your big chip, and then you create layout from that. And when you do that, you will see that each symbol is you will see that each of these things are like different symbols. Or where is it? Yeah. So there are two boxes. One is this one. Another one is the other box that I added. So then you don't see that if the layouts are messed up or something like that. And you can here you can give the coordinate and just adjust them, align them and things like that. And if you want to edit one part of the layout, you just go into this schematic tools where is it? Yes, push into hierarchy edit. You just push into hierarchy edit means that you go into the cell and here you edit something and then you come back, you come up, pop out of hierarchy, you come up to higher level. That means that if 4 persons are designing a big chip, each person has its own cell, they can edit independently and then they don't ruin each other's work, like similar to the way that people design chip. So sorry to keep you waiting from your lunch, and thank you again for your attention and this meeting.
Dariush, thank you so much. Appreciate you joining us from there. Thanks a lot for this insightful session.
Thank you. Have a nice.
Thank you all. Thank you all for this. Okay. May I take a leave from all of you from this meeting? Huh?
Thank you, Professor Amlan. Thank you so much.
Yes.
Thank you.
Thank you. I'm just leaving. Bye bye. Thank you.
Thank you. Take care. Bye.
Right. Thanks, everyone. Bye bye.